Hello, audible?
Yes, sir.
Yeah. Thank you for your patience. Today become delay. So today we start the transformer chapter. Okay. So first we take a here this transformer chapter also categorized in two sections like single phase and three phase. Okay. Just a minute. Yes, please. Is it is audible?
Yes, sir.
Okay. So this transformer is a AC device. Why it is? Because it work on AC only, which is used to change the high voltage low current into low voltage high current and vice versa at constant frequency, means without change of frequency. Okay. So in brief, it transfer the power. Actually, there is a two circuit. They are magnetically coupled. Primary, which is connected to load.
Sir, we are able to see only PPT, sir. If you are writing on the other app.
Yeah. Sorry. See, now this is refer to actually here there is a two circuit. One is a primary main, which is connected to supply side, and load side is called as a secondary. Now your primary side may be HV or it is LV. So always source side, source means when we where we connect the supply, that is called primary, and load side is called as a secondary. Now this transformer transfer the power actually from one circuit, means primary to secondary, at constant frequency, and this is accomplished by a on which principle it works? By electromagnetic induction or mutual induction. Okay, where two electric circuits are magnetically coupled. Now see, we have to understand the mutual induction. Like here one is this is your primary. Here we connect this 2000 volt RMS value. Okay, this is the primary, and here in secondary only 100 turns we get here voltage. We can measure it by voltmeter or galvanometer. Because when we give the supply to primary, there is a flux is produced that link with nearby coil, secondary coil. Okay. Then there is because this is a AC, because AC current produces AC flux. AC flux means changing flux. If your current is sinusoidal, then magnetic field is also sinusoidal in nature. Sinusoidal means alternating. So there is a rate of change of flux. So according to Faraday's law of electromagnetic induction, there is an induced EMF. Okay. So like here, see, this is a transformer here, like primary source side and load side secondary, number of turns. Then there is a induced voltage. In primary, it is a self-induced EMF. In secondary, it is called mutual induced EMF. Okay. Now, construction-wise, if we see, so there is a construction like mainly there is a two type of core we use, like core type and cell type. What is the major difference? See, in core type, we use a laminated core. Okay, it is a stack of number of laminations, means thin plates of iron. Then we put first LV winding. Over this LV we put HV number turns. So actually it is not like only on one limb we put a LV, on other limb we put a HV. We can do like this also, but to reduce the leakage flux. To reduce the leakage flux means, or to increase the mutual inductance means the flux produced by primary, it is link, maximum flux should link with the secondary also, or to reduce the leakage flux. That's why they are overlapped, means we put the over this LV we put the HV winding. Okay. So when we connect but when we study the working principle, to understand the working principle, we consider like on one limb there is a primary winding, on other limb there is a secondary winding, or LV or HV. LV, HV is the technical terms which are used. Like here, core type and cell type both are. In core type, see this light gray color, it is LV winding, then over this LV we put the HV. Like there is a 200 turns suppose. Then first we put 100 turns on one limb, 100 turns on other limb of LV winding. Over this we put the HV number turns, half of HV here, half of HV. And on cell type, there is only the winding is carried out on center limb. Now see, we use the laminated core. But what is the cross-section area of the core? Actually, it is rectangular, circular, or maybe square core. Circular, to make a circular core is very difficult because very number of multi-dimension stampings we required. So multi-stepped core we are used. Why? This is another method to reduce the leakage flux, or to reduce the leakage flux and leakage reactance. Okay. We use a laminated, multi-dimension core, okay, or cruciform core. See, when leakage flux or it reduce the filler material requirement, okay. Cell type, then oil type transformer. Okay, there is an oil type conservator tank and breather. Silica gel filled with silica gel breather is there, and oil is filled. But generally on board we use a dry type. Now if we see the working principle, as we connect the primary to alternating source, there is a alternating flux is set up in the core. That flux is linked with primary and secondary as well. So there is an induced EMF in primary and secondary. Okay. When we connect the load on secondary, there is a load current is flow. But when we connect the load, the primary current is increased. Let us, by this is the simplest diagram is shown here. Okay. My dear, if we talk about the transformer, so first of all, we discuss the single phase transformer. You know, this is the magnetic core of transformer. Okay. Okay. I am talking about if we see the cross section area, cut section of this core. So if suppose it is a square core, square section, like this. Then when we do the winding over this, okay, winding over this, like this. So there is a ear gap. See, this is the ear gap. Okay, correct. So in this, it required to fill the filler material, wood like this. Okay, to make this winding circular inside. Second, in this now there is a leakage flux, because maximum when see, suppose this is your primary winding here. We want, okay, like this. This is your primary here. When it is connected to your alternating source, AC source, okay, like this. So you know, it is AC means Vm sin omega t. Okay, dear. Sinusoidal voltage. Okay, like this. This is this kind of supply. Okay. So here current, if you apply a sinusoidal voltage, then current is also sinusoidal in nature. When this sinusoidal current is flow past to this core, okay, there is a magnetic flux is set up in this core. Okay, core, like this. This is the magnetic flux phi is set up in this core. Okay, phi. The maximum flux is confined within the core, because it why this core material is, hello, this core material is soft iron. Soft iron means it is soft means it is not a like a softness. No, soft means it is a now magnetic material are categorized: soft magnetic, hard magnetic material. So generally we use a silicone steel laminations. Okay. Iron core. Now why we use this iron core? Because soft iron core or silicone steel, it has a, you know, relative permittivity, permeability. It is 1,000 times or 10,000 times as compared to paramagnetic material. Okay, so it has a high permeability, low reluctance. It means easily it is like your flux is flow in the core. Okay, so it provides low reluctance path. Okay, so maximum flux is will flow this low reluctance path. Okay, like current is flow in the low impedance path, same like here. Now, but some flux, now what is, how this direction is upward here, upward like this, in this direction. Hello? By right hand thumb rule, if we hold the coil in your right hand, see this direction of your finger represents the direction of current, then your thumb. If the thumb is indicate the direction of
field of flux.
Magnetic, yeah. So your field is here upward. Then it is circulate within this core because it has a low reluctance path. But some flux is come in this side also, like this is due to frinking effect, okay, magnetic frinking effect, okay, like this. This flux is called leakage flux, leakage. It is not linking, it is a leakage, my dear, leakage flux. Okay, leakage flux means why due to this leakage flux there is a leakage reactance. Okay, so due to leakage flux, there is a inductance is leakage total leakage flux divided by per unit current, then it is an inductance in Henry. Then due to inductance there is a leakage reactance. Okay, dear. So if there is a leakage flux, there is a leakage reactance. Got it? So there was why I am putting on this, because in your question that is asked, what is the how we reduce the leakage flux, leakage magnetic field, then how it impact the performance of transformer. If see, if higher the leakage flux, high will be your leakage reactance. Then there is a this impedance is impedance total, like your total resistance as referred to secondary side, total leakage reactance as referred to primary side. This is your impedance, Z02. Now due to this there is a drop, voltage drop. Your regulation is value is high, means poor regulation. High voltage drop means actually regulation is nothing but it is the percentage voltage drop. Okay, so higher the leakage flux, higher will be your leakage reactance, then for your regulation. Regulation low value is good. Okay, now same like here in secondary also. Okay, like this is your secondary winding. Okay, here this is your secondary. Okay, suppose this is your secondary. Now if it is open, then there is a induced voltage E2. Here it is, we apply the V1 voltage, but here in the self-induced EMF is E1. Now suppose we put the load here, then there is a load current is flow I2. Okay, now it depends what is the power factor of this secondary load current, then it is lagging or leading. But when this current is flow, there is a drop. Due to drop, then now this terminal voltage become V2 from E2. So E2 is induced voltage, and V2 is your output terminal voltage across load terminal. Okay, correct. Now due to this current, when this current is flow, due to this current there is another flux is set up. Now due to this load current, another flux is there. What is the direction of that flux? It is opposite to this. Opposite to this. Now we assume that in the transformer this flux should be constant. So to maintain the same flux in the core, what will do? Your transformer draw more current from primary. Okay. So earlier there is a no load current it is taking when there is a no load, but when this load is put, then this current will increase to I1. So now this increased current will produce more flux in the core. then this is neutralized and your flux is maintained constant. So momentary, when we put the load on to transformer, what happens? The flux is reduced, then immediate your primary current is increased to maintain the same flux in the core. Okay. So sometimes the question is asked, when we put the load or increase the load on secondary, why the primary current is increased? To maintain the constant flux in the core. Because your secondary current is opposite direction, it produces the opposite magnetic flux. Okay, correct na? You apply the right hand rule. Then see your secondary, due to secondary current, there is an opposite flux. Okay. Okay, dear. So now due to this secondary also there is a leakage flux, my dear. Like here, franking effect. So there is a due to secondary leakage flux also. Okay, dear. Correct. Now so this is the working principle. The EMF is induced. Okay. Then now you come to the EMF equation of transformer. EMF equation of transformer. See, actually, as we connect the primary to source, you know, their flux is directly proportional to current. If your current is sinusoidal, so you are see your magnetic flux. See, this is your omega t, suppose. So your flux is like this. Sinusoidal flux is produced here. Okay, this is the phi m, maximum flux. Okay, so this is the flux. Okay, phi. Correct. So here, you know, induced EMF E equals to according to Faraday's law of electromagnetic induction, E is directly proportional to d phi by dt. Okay, d phi by dt, or E equals to minus n d phi by dt. Correct, no? Now if we put the value of phi, d by dt of, now we put here phi m sin omega t. Correct, because this equation of this, it is sinusoidal, no? Phi equals to phi m sin omega t. Okay, please you derivate this, then it comes, hello, minus n phi m maximum flux. It is a constant. Then you know derivative of sin omega t. It is cos omega t. Okay. But with respect to t, then omega is also multiple here. Okay. See, then omega t is omega. Omega is multiple here. Okay. It is minus, no, actually minus cos.
So can you explain why did we take that as minus n?
Okay. Minus is due to Lenz law. It opposes the cause of minus due to the polarity of induced EMF is oppose the applied voltage. That's why it is negative. Okay. It is negative is due to it is minus always, because why we take a negative is by Lenz law. Lenz law is state the what is the polarity of induced EMF. It opposes the supply voltage. That's why it is negative polarity. Okay. Derivative is come minus. Hello. This come minus n omega cos omega t. Okay. Then you know this cos omega t we can write minus n phi m omega. Cos we can write sin pi by 2 minus omega t. Okay. Hello, this cos omega t we can write this. Then this minus is go inside, then it becomes sin omega, sorry, pi m omega sin. This become omega t minus pi by 2. Okay. Correct. E equals to. Okay. Now this is the induced EMF and ET. Okay, this is equation 1. Now when this actually it is we can write it is a E, E induced EMF. Now E maximum. So when you know omega t minus pi by 2, this angle is 90 degree. Then sin this sin, then sin omega t minus pi by 2 will be 1. Then this flux is, it is a maximum. Okay, maximum value will be phi m omega. Okay. N is also there. Okay, n we forget no n here. Here it is n phi m phi maximum omega. Here it is n phi m omega only. Okay, this maximum flux. Now you know omega value is 2 pi f. Okay, omega n and phi m. Okay. Now this is your maximum value. Okay. This is your maximum too. Now you know. Now we can write na E equals to, if we calculate E equals to E journal or it is a like sinusoidal na E. Actually this is maximum or this is E only. Okay, you write this. Now this comes E equals to E maximum sin omega t minus pi by 2. Okay, this sinusoidal. Then if we put here value, now if we calculate RMS value, okay, so this will give you third. Now RMS value of induced EMF, that is E equals to RMS value E or I RMS you can write. Okay, E RMS. That is, you know, VM E maximum by root 2. Okay, so RMS value we represent by capital E. Okay, it is not required to write RMS. Okay, then it is what is your E maximum? E maximum is 2 pi f n phi m divided by root 2. Then it comes, okay, then by this equation now your E induced voltage is come, you know, 2 pi, 2 into pi means 3.14 divided by root 2. then phi n fm. Okay. Now this value will give you 4.44 phi m f n. So this is your induced voltage, my dear. Okay. Please. This is the induced voltage or EMF equation of your transformer. Okay. N is the number of turns, F is supply frequency, phi m is the maximum flux. Okay, dear. This is the your induced EMF. Okay. So equation 4 will give the induced EMF in your generally induced EMF. Okay. Now let us therefore induced EMF in primary E1 equals to 4.44 phi m f n1. Okay, this is 5 and mutual induced EMF in secondary E2 equals to 4.44 phi m f n2. This is 6. Okay, so these are the induced EMF equation. Okay, dear. Now we discuss come to the transformation ratio or turn ratio. It is called turn ratio of transformer. Turn ratio. Okay, it is denoted with K. Okay. Now from equation your 4 and 5 now 5 and 6. So if your equation 5 from equation 5 and 6. Okay, if they divide, your 6 is divided by 5, then you know common part is reduced, only it comes n2 by n1. So this is 7. Okay, correct. So if this equation this 5 and 6 are divided here, so these common terms are cancelled, only n2 by n1. Okay, now 4 you write here, 4 ideal transformer. Transformer means loss free. Ideal means loss free. Now for loss free transformer means the entire power from primary to transfer to secondary. So your primary volt ampere. Volt ampere is power. Okay, V into I or kVA. Primary kVA equals to secondary kVA equals to secondary volt ampere. Okay, it means V1 I1 equals to V2 I2. Okay. Then V2 by V1, see this come this side, equals to I1 by I2. Okay, you write it is 8. Okay, correct. Now actually no load current in transformer is very less. Okay, so if no load ampere turn means 80 ampere turns means mmf. Ampere turns is mmf, magnetomotive force, are neglected. Then you can write primary ampere turns, MMF equals to secondary ampere turns. Okay. Ampere turns means N1 I1 equals to N2 I2. Okay. Or we can write N2 by N1 equals to I1 by I2. So this is 9. So if you combine if you write here by combining equation 7, 8 and 9 and 9. Okay. 7, 8 and 9. So these are all equal now. Therefore turn ratio K equals to E2 by E1 equals to V2 by V1 equals to I1 by I2 equals to K. N equals to N1 by N2. N2 by N1
and 2 and 1.
equals to K. So this is your turn ratio. Okay. This is the turn ratio of transfer. So please remember this turn ratio. Okay. And EMF equation of alternator was asked. The same they can ask the EMF equation of transformer. So no derivation, at least you remember this induced EMF. Okay. Let's see. So this is your
Sir, please show this 5th and 6th equation, sir.
EMF equation. Yes.
That's it, sir. Wait a minute. Okay, sir.
Now I am coming to again from this practical diagram. We can draw the equivalent. If we talk about the equivalent circuit, of transformer. So first we taking the single phase, because 3-phase transformer also we do as a per phase. Okay. So of single phase transformer you can write. Okay. So dear, as I told, because your primary winding is consist of wire, it has a winding. So there is a resistance of primary winding. Then there is a leakage reactance. Now, this is the primary leakage reactance. Then there is a magnetizing core or circuit. Same like in 3 induction motor. So this is your magnetizing core. Now this is the now it is ideal transformer we consider here. Okay. Okay, due to this, there is a core. Then this is secondary, same like secondary resistance, secondary leakage reactance. Okay. Now suppose it is open. Okay. Now here when we apply the voltage V1. Okay. Then actually there is no here this secondary current I2. This I2 load current is 0. That's why here this is the secondary load current as referred to primary side, or effect of secondary load current on primary side, this I2 dash. This will be 0 at no load. It means this transformer draw only the no load current here. Okay, here only. This is 0, then this entire current goes here. It is a no load current. Now this has a two component, this I naught. Active component and passive magnetizing. This is your loss component. Okay, it is a magnetizing branch resistance, magnetizing branch reactance. Okay, now this is at no load, this I1 equals to I naught only. But okay, now when this current is flow, magnetic produce a magnetic flux, then there is a induced EMF E1. Okay, generally at no load there is a very low, it is a R1 X1. This is R2 X2. Okay, or it is Z1, combination of resistance and reactance. So actually at no load what is the drop in this primary? I naught Z1. Z1 means it is a R1 plus X1 whole square, like this. Okay, correct na? So it is here, this drop is very less. Then at no load we can assume like V1 is near about the E1. Okay, if we neglect this primary drop, but on load it is considerable. Okay, we have considered this drop. Okay, then actually which is greater? E1 is less than V1. V1 is greater. Okay, now
सर एक मिनट सर, ये I2 डैश को जो 0 माना सर, एक बार जरा पॉइंट रिपीट कर देंगे सर, क्यों 0 माना है सर?
I naught is not 0 here.
सर I2 डैश
I2 dash, because here this 0 load current is 0.
Okay sir.
Then the effect of load, if as we put the load on secondary, primary current increase by this factor. So but if there is no load, means this is 0. This only at no load, this is the current only here, means at no load transformer draw only no load current.
Okay sir.
Isliye there is a difference at no load and full load condition. Okay
sir. Okay.
Suppose now if we put a load here, now load may be, generally it is not pure resistive, like it is an inductive like motors. So we consider it is a lagging power factor, means your secondary side power factor is cos phi 2. So let us, it is a lagging power factor. If there is a capacitive load, it may be leading also sometimes. If we put a pure resistance load, it is a unity power factor load. So this cos phi 2 is not a transformer power factor. It is a load power factor, my dear. Okay. But this load is decide the overall power factor of transformer, that is cos phi 1. Cos phi 1 is your primary side power factor, that is the overall transformer power factor, correct? Okay, so now this current will be there, it is not 0 now. Okay, it is I2. Then there is a as referred to primary side, this is your load current. Now in this condition, your primary current will be not I naught only, it become I naught plus I2 dash. At this node you apply KCL, incoming current equals to sum of this outgoing, I naught plus I2. But my dear, this it is not a algebraic sum. ऐसा नहीं कि suppose this is a 5 ampere, this is 2 ampere, 2 ampere, this is 5 ampere. We add like 7, this is 2, this is 7 ampere. No, they are out of phase, means they are not in a same phase. That's why they have a different there is a vector sum. Okay, this is has a vector sum, like vector sum of okay. It is a vector sum. So this is the at load. This is at load. Okay, at no load, I1 equals to I naught only. Correct? Okay. Now here is the secondary induced EMF. Now when there is a load current, there is a drop in this impedance also. Then this voltage is reduced to V2. Okay. So it is a load terminal voltage. Okay, dear. Okay. Now if we talk about the voltage regulation of transformer, it is nothing but suppose there is a no load. If we remove this load, then this voltage is now open terminal voltage is there is no drop. It means this is equals to E2. Okay, so this is no load terminal voltage or induced voltage minus when we put a rated load here, full load. Okay, suppose here full load is connected here. In this condition, this terminal voltage now in this case it is not as E2, it is reduced to V2. Then full load voltage divided by full load as a percentage change. So this voltage regulation is nothing but it is the percentage variation or percentage change in output terminal voltage of transformer from no load to full load. That is represented as a percentage. Okay, that is called voltage regulation. Now actually it depends on this power factor also. It is a unity, lagging, leading also. Okay, that we discussed this in detail, this voltage regulation. Okay, but now this equivalent circuit, now we again extend it. Now suppose this prime secondary side or this primary side we can transfer to secondary side, or sometimes this secondary like this secondary side is we refer to primary side, then it become, see, this is a primary resistance, primary reactance, and there is a, this is your magnetizing branch. Okay, now see, if you transfer this data, here it comes R2 days, then this become X2 days. Days means age refer to primary side. Okay, okay dear. Then this load impedance also, this load we have also transferred, no? So it become now ZL days. Here it is ZL only. Now this terminal voltage also be 2 days. Okay dear. Here it is E2 days also. Now but E2 days is, you know what is the voltage across this here? Here it is a E1, na? So equals to E1. Okay. It is R0, X0. Here it is 2 component I omega I mu magnetizing current. This is I naught. Here it is I1. This is R1, X1. Okay. Here it is I2 days. Okay. Now here we apply the voltage. Okay. That is V1 primary voltage. Here it is E1 only. Correct? Same like this. And here this is I1. Got it, my dear? So as refer to, here it is as refer to primary side. But sometime we can refer to secondary side also. then this become dash dash, this that goes this side. Okay, now let us now see, my dear, this is the magnetizing branch. This is your magnetizing branch. This branch, it is responsible for your core losses and magnetic flux. Core losses. Now you know, actually this is core losses. They are depends on your frequency now and voltage. Okay. So actually there is a as I told, suppose this V1 and V2 is very close. Actually this is your exact equivalent circuit of transformer. But when we now we do some modification for simplification analysis. What we do, we consider this V1 equals to E1. If we transfer this magnetizing terminal at the supply end here, okay, then in this case, in that case, this two resistance are come in series, they are add. These two reactants are come in series, okay, they add. And this is your magnetizing branch here. And this is your load. Here it is your V1. V1 and E1 are same, we assume. Okay. Now this is I1. Here this is I0. Here this is I2 dash. Now here R01, X01. And here it is your E1 equals to E2 dash. They are but they are equal to B also, we assume. Now due to this, there is a drop in this impedance, and this terminal voltage become V2 dash. Okay. And this is your ZL dash. Cos phi 2 is the load impedance, power factor. Okay. So what is the R01? R01 is the total equivalent resistance as referred to primary side. X01 is total equivalent reactance, my dear, reactance. Then Z01 equals to total equivalent impedance, R01 square plus X01 whole square. Okay. Now, how we calculate this dash dash? See, we use certain principle actually. So as you know, if you take a turn ratio actually, now actually in ideal case, as I told now, this I0 is very less, we neglect it. If we neglect this I0, actually I0 if neglected, then your I1, turn ratio, by turn ratio, I1 by I2 equals to N2 by N1 equals to K. Okay. So this we can write, this become I2 dash by I2 actually equals to K. This is for this is your for, this is actual practical transformer, actual transformer के लिए, okay? But this is in ideal case. We neglect the I0 in this case. Okay, this is for ideal, because we assume now when we calculate the turn ratio, This is for ideal.
I2 days by I1 होगा ना सर वहाँ पे?
Sorry, yes.
Equal to K में
No,
जहाँ
no.
लिखा है
No,
I2 days upon I1 या I2 days upon I2?
Actually, here you see, if we neglect this, I1 equals to I2 days.
Okay sir.
Here
Okay,
we
okay.
replace I1 equals to I0 plus I2 days. It means
Okay.
this neglect, then it is become I1 equals to I2 days. I2 days, okay, this. So here, this is actual here. So my dear, now you know, if I0 we neglect, then it is a if we calculate I2 days. I2 days equals to, please. Now we can calculate now here, I2 days. Hello. Now I2 days become, sorry, I2 days. I2 days equals to KI2, correct? Okay. So yeah, this I2. And you know, current is multiple and E2 days equals to E2 by K. See, you know, because we write na E2 by E1 equals to K. But you know, here in this case, we take na this E2 by E2 days. Because here we assume na E1 equals to E2 days. So it is a K or E2 days equals to E2 by K. Please remember, hello, when we transfer the data from as referred to means primary to secondary side, your current is multiplied by turn ratio, your voltage is divide, okay? Or like same we can write V2 equals to V2 by K. Next, other things. Now we talk about this is the current and voltage. Now we talk about resistance and resistance. You know, actually a total copper loss. Please calculate the total copper loss of transformer. There should be no constant. If you modify the circuit, this losses should not affect. Correct, no? So that your performance do not affect. This total copper loss means, no, this is I1 primary copper loss plus secondary copper loss. Correct, no? Okay, dear. Okay. Hello. Primary copper loss plus secondary copper loss. Now, as referred to primary side, if we take a total resistance R01, then primary side current I1 square only. See here. Actually, I0 we neglect, na? So here I1 equals to I2 days. Okay. I1 here it is I1. This is the resistance. This is the total resistance. Hello, this is total resistance. What is the losses here? I1 square R1. This is the total. Huh? Now, if we calculate R01, then your I1 divided by this, it is R1 only plus. If this divided by this I2 by I1 whole square R2, or it is R1 plus I2 by I1 is the 1 by K square. Okay, K square R2. Or my dear, it is R1 plus R2 by K square means it is R2 days. Sorry. Now this become R01 means R1 plus, it is denoted by R2 days. So what is the R2 days actually? Hello? R2 by K square. So your resistance is divided by K square. Same like your reactance. Now reactance also same kind of. Now this is X2 days is also X2 by K square. Z2 days equals to Z2 by K square. Hello, any doubt here? So actually these things are required when you calculate regulation, this how to convert this R2 days, X2 days, how we calculate, okay? So this is coming from this, okay? What is R2 days? Okay. But now if we write as refers, please remember this is very important, refers to secondary side. If we transfer the primary parameter to secondary side, okay, H refers to primary side. So H refer to primary side, in that case, it is just opposite. Even days in that case, even days becomes equals to, it is multiple K even, and I1 days become current is multiple, here it is divide I1 by K. Just you check, and your resistance I1 days become, it is multiple by K square R1. X1 days, again it is K square X1. Okay, V1 days equals to, it is K times, current is divided. So current, now voltage is multiple, K V1, okay? Okay, dear. Even your this R01 also days, X01 also days, okay? This R will also change, okay? Because here this primary circuit, hello, ये जो primary parameter है, this transfer to secondary side. Okay, dear. Hello. Now, if we draw the equivalent circuit as refers to secondary side, secondary side. So my dear, this is the secondary side. So this is your secondary total resistance. Total resistance, total reactance, okay, and here is your magnetizing branch. So you know, my dear, what is the voltage here? E2, correct, no? And here it is, you know, it is a, here it is I2, correct? Here it is I1 days, I1 days, okay. This is your I0 days, here it is days, okay. I omega days, I mu days. This is R0, X0 days, magnetizing parameter. But this is your total resistance as referred to secondary side. This is total reactance as referred to secondary side. And this is I2. Here, load side, cos phi to ZL. Across this terminal, this is V2. Okay? Okay, dear. Hello. Now these are the total resistance and total reactance. You know what is the voltage here? E2, no? Correct. And here it is V2. So there is a drop in this impedance and resistance. Okay. due to this current I2. Suppose it is lagging. Okay, dear. So what is the R01? Sorry, R02. R2 plus R1 days. Now you know R1 days equals to K square R1. Please remember. And X02 equals to X2 plus X1 days. You know X1 days equals to K square X1. And K is the turn ratio. Okay. Any doubt here? Hello? Any doubt here, please? Okay. So my dear, this is the total leakage reactance. This is total. This is your total resistance, equivalent resistance as referred to secondary side. This is total leakage reactance. Okay. So now due to this, it is due to leakage flux. Now, got it, my dear? Any doubt here? Equivalent circuit and this. Hello? Now again come to here our you know your equivalent circuit. Hello? Exact equivalent. It is, see, this is approximate equivalent circuit. This one has referred to primary side and this one has referred to secondary side. This is approximate. Why here it is approximate? These are approximate, okay? Because here we shift this magnetizing branch. Actually, it was between the primary and secondary impedance, okay? But we have considered as a supply end. Now, what do you know? Exact equivalent circuit was? This is your exact equivalent circuit. Okay, dear. But here, if we see the exact equivalent circuit as exact is, this is your primary resistance, this is primary reactance. Then this is your magnetizing branch. Sorry. As referred to primary side I am making. Then this is your secondary resistance, secondary leakage reactance. Suppose it is at no load, okay? But here we apply the voltage V1. Then this transformer take a no load current. Only I1 equals to no load only. This is R1, this is X1. Here this is I0. So this I0 has a two component. Loss and magnetizing component. R0, X0. Okay. Here, this is actually at no load, it is 0, I2 days. But here R2 days, X2 days is also there. Okay. Suppose it is at no load, then this voltage E2 days, or at no load, this is equals to V2, no? Now here it is E1 days. Now, if we talk about the ideal transformer, my dear, ideal means ideal transformer. Ideal means what? It 100% transfer the primary power to secondary. There is a 100% coupling between primary and secondary. Zero leakage flux. Now, if zero leakage flux means this reactance, primary and secondary leakage reactance will be zero. This is windings are with high copper conductor, high grade copper conductor. The resistance are zero. Losses are not there means resistance are zero. Core losses. So see this resistance, no, actually this are if we calculate, no, this represent the core loss. So this core loss is also not there. Means 100% flux is in the core only. Okay, so magnetic losses also not there. Copper losses are zero. So this branch is also zero. So what is the equivalent circuit of ideal transformer? Can you draw? My dear, this is the equivalent circuit of ideal transformer. This is. Okay, dear. So when you apply here voltage, there is a, now it is at no load. That's why here this current is only this, but here it is only magnetizing current. Okay, I mean, because this branch is not there, only this. Okay. So yes, I mean only magnetizing current. Okay. Here only it is a magnetizing current. Okay. I mean, this is Ix naught. Okay. Now actually at no load, this is I1 equals to I mu only. Okay. Because it is, and here it is induced voltage E2, here it is primary induced EMF. Now because here impedance is not there, then this V1 equals to E1. Now if suppose we put a load here, suppose if we connect the load on secondary of ideal transformer, okay, now this terminal voltage become V2. But you know, here internal impedance we have neglect, no? Here no resistance, no resistance. Then this induced voltage here, induced voltage equals to terminal voltage. So your secondary or primary terminal voltage are equals to induced voltage. Both are equal, correct? Then if you assume this is your load current, because it is a cos phi 2. Now it depends what is the power factor. Then this is I2 is there as primary side. It is a days, because it is a, we have as referred to primary side. So this is your load current. Now in this case there is not I mu, it is I1 in this case at load. But at no load, your ideal transformer is this much only. Okay. Okay, dear. So this I1 is only equals to I mu. So see, actually, if you look this circuit, it is like this, like a pure inductor. This is like pure inductor, and which is connected across a AC source, because here we apply AC sinusoidal voltage. Okay, this way, and we measure the voltage across this output terminal here. These are okay. So let us see, when we apply here V equals to Vm sin omega t. So there is a current I then in this inductor. Now this induced voltage here, across this induced voltage, you know, this induced voltage, or here it is a E1, E1, and here it is E2. Okay, second thing. So basically this in pure inductor, hello, let us see. So if you draw the vertical axis, please, very important, please look at this. This is a vertical, this is horizontal axis, okay? Am I did? This is vertical, this is horizontal. This is graph paper. Now, my dear, at no load, so we first consider ideal transformer at no load. So at no load, you know, ideal transformer, it is a inductive only, highly inductive. Okay, so suppose here, suppose this is your supply voltage V1. Now you know current is lag by 90 degree. So your magnetizing current is here on this. Sorry. So my dear, this is your magnetizing current. This is your magnetizing current, okay? Actually, we make it is dot, and okay, dot. This also you make this dot. But this is suppose your supply voltage V, okay? V1. Suppose this is your supply voltage V1. Due to this V1, your this current, magnetizing current, this current in pure inductor, it is in phase with, it is 90 degree lag, okay? This. Now it is a magnetizing current, means what is the purpose of it magnetize the core, it produce the flux. And you know, this is in phase with current. You know, flux is directly proportional to current. Okay, so this flux is in same axis, it is in phase. Okay, now this magnetizing flux induce the EMF in primary and secondary. So here there is a voltage are induced here, E1 and E2. Now it depends on number of turns. This is your suppose E1 has a number of turns more than E2. Okay, they are in same phase because they produce by same flux. No, only number of turns are different, like minus n d phi 1 by dt. Phi means this flux, phi d by dt. d5 by dt, n1. Sorry, it is 2, 5, and it is n2. No. Flux is same. n2 d phi 1 by dt. Okay, this is my n1 d phi 1 by dt. Okay, it is a phi 1 flux. Here it is also phi 1 because flux is same. Number of turns. It is negative because it is opposite to V1. That's why it is polarity is opposite. So see, actually your induced voltage are at 180 degree. They are opposite. They oppose the supply voltage. That's why their polarity is opposite to supply voltage. Okay. Why they are at 180 degree? Because they have opposite to. Okay. Correct. So this is the vector diagram of, and this is I1. This is the vector diagram of ideal transformer at no load. But suppose, my dear, if we connect the load, now ideal transformer at load, please consider. So there is a load current is also there. Okay, and suppose power factor is lagging power factor. Okay, load is lagging power factor. Okay, it means this is now because but we have considered there is no impedance in secondary and primary, means there is a no drop, so it is V2 and this is minus V1. Correct? They are opposite. Now this is your V2. Suppose this is your V2 voltage. Now this is your V2. Okay, here. Now this secondary load current is lag this by, because it is less than 90. It is lagging. This is your I2. Secondary load current is lag with phi 2. Hello, cos phi 2. Suppose it is 0.8. Then phi 2 we can calculate. It is cos inverse of 0.8. Then we can calculate sin phi 2 also. Same like no load power factor cos phi naught. We come later on. So see, this is your I2 load current. Now as referred to primary side, actually this is secondary side. This quadrant is secondary. This is your primary. So on primary side, this is your as referred to primary side. This is the current. Now this angle is same like this phi 2. Okay. This is I2 dash equals to KI2. Now vector sum of these two current. Okay, my dear, this two current. This is your primary current at load I1. Now the phase difference between V1 and I1, it is phi 1. So this I1 is your primary current, okay, load current, and cos phi 1 is your primary power factor. Okay, dear. Okay. Now we do some other, like we take some partial ideal transformer. Means just only we neglect the impedances, primary and secondary impedance, but we consider the complete magnetizing branch. Suppose your magnetizing branch is completely here, means core losses are there. Okay. When we apply this voltage, okay, and suppose secondary we kept open. So when we apply voltage, this transformer take a no load current from supply, like this. Okay. Then this no load current is have a two component, loss and magnetizing. This is R0 X0. Okay. So here I1 equals to I naught here. Okay. But at no load, this is the transformer at no load. So my dear, please tell me what is the no load input power? No load input power. My no load input power equals to V1 I naught cos phi naught. No load power factor. Okay, this is the power, and it is considered as omega naught. So sorry, W naught. That is no load power input equals to, it is equivalent to total iron losses, core losses. because at no load we get a zero output. Then where this power is goes, goes as a losses. So in open circuit test, what losses we measure? Core losses, iron loss. Okay, dear. So this is the core loss or iron losses. Iron losses. Correct. Basically, here we neglect the copper losses. So now from this diagram, you can calculate a cos phi naught, no load power factor, of transformer. That is core loss, this no load input power divided by V1 I naught. Or phi naught we can calculate cos inverse of this. Then sin phi naught we can calculate also. Okay. Okay, dear. This is the now two component of I naught. There was a question is asked. So I naught has a two component. One is active or loss component. Second is passive or magnetizing component. Okay, it is denoted by this. This is omega mu. Now you know. Let us come. Okay, so in this case actually, so at no load, this power factor of it is highly inductive. Your transformer at no load, highly inductive means this power factor is very low. Then angle is large. Okay, if power factor low means angle is large. So my dear, in this diagram, now if you draw for this, so again you assume like vertical axis. This is suppose your voltage, supply voltage V1. Okay, now suppose this is your horizontal axis. Okay. Now, you know, at no load, your no load current is lag with this V1 voltage at very large angle. So this is your large angle, phi naught. Now here, this is I naught. Okay, my dear. Now it has a two component. Hello. It is I naught cos, sorry, this side is cos naught. Angle side, it is always cos. I naught cos phi naught. This is I naught sin. Hello, this is I naught sin phi naught. My dear, this is I mu, magnetizing current. This is, okay, so this two component is I naught cos phi naught. This is I naught sin phi naught. Please, you can calculate these two component. यहाँ तक समझ में आया? Are you understand up to here? Because the question is asked on this. Okay. Hello. Okay, dear. V1. Then your current I naught is lag with angle phi naught. No load current. It has a two component. Now this magnetizing current, this mu, it produces a flux in the core. Okay, phi m, magnetizing flux. Then it induce the EMF, voltage in primary and secondary. Okay, so this is E1, E2. Now, as you know, there is an impedance are neglected. Now, impedance are not there here. So drop is 0. It means there is a, now suppose load is there. Hello. If we connect a load here on secondary, hello. If we put a load, then this terminal voltage become V2. But you know, if there is a no impedance here and here, then this induced voltage E2 equals to V2 and this induced voltage E1 equals to V1. Okay. Okay, if impedance are neglected. it means this is your V2 and this is your minus V1 because it is opposite to, it is opposite, no? At 180 degree. Now, due to this secondary voltage, secondary load current, hello? Suppose this is a load, my dear, this is a cos phi 2, load power factor is lagging. Load, then there is a load current I2. Actually, as referred to primary side, it is days, but we are considering as like here, this secondary side. Then it is I2 dash, but this current is lag with, sorry. Hello, this is your secondary load current, here, this I2. This lag with phi 2. Okay. Now, as referred to primary side, this is your I2 dash. Actually, this is the same angle, phi 2. Now, my dear, in transformer, please look here. Hello. This is your I2 current or I2 dash. This is I node. Here at this node, this is I1. Now it is not I0. I node, it is I1. So I1 is the vector sum of these two current. Hello. So your vector sum of these two current will be this. Hello. This is your load current, primary load current. Okay. This is your phi 1. Okay, so this is your I1 is your primary current. Cos phi 1 is your primary power factor. Okay, dear. Any doubt here? Hello? Any doubt? ये आप याद रखिएगा प्लीज, इट इज वेरी इंपॉर्टेंट है. Yes, please. Okay, put this diagrams here. Okay, dear. Here there was a question was asked in this. That's why we are discussing here. Okay, how this discuss here the questions. Let us come to. In September, October, November. See here. Hello. This was a different question, but here, see, one question was there. What is the leakage flux? How it is possible in iron goes? How we can take into account of analysis of transformer? We are discussing this, and this voltage regulation. Tomorrow we discuss this, but I am looking some other question. Just a minute. October month.
October month, sir.
Yeah. Here. This is one question. A 230 by 115 volt single phase transformer supply with a load of 5 ampere at this. So this is the secondary current I2 at cos phi 2. And no load current is, this is I node. At no load power factor cos phi 2 is 0.2 only. So as I told now, at no load, very low power factor. Calculate the primary current and primary power factor. So this is the question we solve with this, okay, here by this method, this only. I1, I2, V1. So tomorrow we discuss these questions, okay? Just a minute. Okay, dear. Good night. See, yes, next slide is your ideal transformer. Zero flux, winding has no resistance, core is infinite permeability, core layer, magnetic loss free. Okay. Good night.
Good night, sir.
Good night.